are in listen-only mode.
Good afternoon, everyone. Appreciate everybody joining us this afternoon. This is the 7th of 8 sessions for our Performance Palooza event today. So we appreciate you joining us here. Just a little bit about us. If you haven't heard about us today, my name is Ryan Adams. You can follow me on Twitter. It's at ryanjadams.com. I am the president of the chapter. You can follow the chapter itself. We've got a Twitter handle you can see there. And we also use the PastPVC hashtag if you want to tweet and talk about the session or the event today. We do have monthly meetings. If you're not a regular member, you can go sign up out at performance.sequelpass.org, or you can even join our discussion list, and we'll send emails out to both of those lists about our monthly meetings. That way you can join and take advantage of those. Also, that Google group list is open and it's public for anyone, so if you've got a performance-related question, you can shoot it out there, and you'll usually get an answer, so take advantage of that free resource. We are using GoToWebinar for our platform today. It does have a panel. As we start the session, the panel will probably slide over and kind of hide itself on the right-hand side. You can click the red arrow at the top and it'll expand back out. That way you can see all of your choices and options there. And at the very bottom of those is going to be the question pane. So if you have questions about the session as we go through those today, just type those questions in down there at the bottom and we'll get that captured and try and get you some answers there. If you're having a hard time seeing, things aren't big enough for you, there is a zoom button on the presentation window, so you can use that as well. Reminder is if you're joining here and reading the slide, you'll see that we don't have a dial-in number. The audio is only through your computer speakers today. We do want to make sure we thank our sponsor, SolarWinds. SolarWinds is the only sponsor that we have for our chapter, and thanks to them, as it allows us to bring all of these 8 sessions to you today and our monthly sessions to you every single month. So we want to thank them for that, and they were so gracious that we were actually allowed to give away a $50 Amazon gift card to a random person out of everyone that attends in every session today. PASS Summit is coming up this October, last week in October. If you're going to attend, I will be there. In fact, everybody at the virtual chapter will be in attendance, so make sure you say hi to us and find us. We'd love to meet you and talk to you about the things that you're doing performance related. If you're going, use our chapter code down there at the bottom, the VC15LHW9. That is posted on the homepage of our website, so you can go to our website and grab that code anytime you want. That'll save you $150 off registration, so take advantage of that as well. Again, we are in the 7th session for the day. So I've got my friend Tracy Jordan here about to talk to us about troubleshooting on secondary replica latency with availability groups. If you want to register for the last session, Mike Fowle is going to be talking about some PowerShell stuff and how to benchmark SQL Server with that. You can go hit performancesequelpass.org and sign up for the last session there. So with that, let me change the presenter over to Tracy. All right, should let you share. Looks good.
Great. Thank you, Ryan, for the intro. My name is Tracy Jordan. I am a Senior Technical Advisor with SQL Server Support at Microsoft. I am glad to be able to present to you today and would appreciate any feedback that you have. Just to give you a little bit about myself, I've been working with SQL for about 20 years, spent both as a database programmer, admin, working for banks, online companies, things like that. I've been with Microsoft for about 9 years in various roles. I've been a dedicated PFE before, MCS consultant, and currently in my current role in CSS and support. Just a quick shameless plug, I will be doing another presentation for PASS this fall at the summit, finding the root cause for unexplained availability group failover. So if you happen to go to the summit, look forward to seeing you there as well. Thank you very much. So with that out of the way, let's go ahead and get into this. What I wanted to chat a little bit about today is secondary replica latency, and what do we mean by that? Probably one of the most common definitions of this is I can't see my data on the secondary that I've committed on the primary. I've seen it, I've committed it on the primary, but I'm not seeing it on the secondary. Log send queue buildup, essentially getting the data over to the secondary, and we'll talk about some of the causes for that. This presentation won't go into resolutions so much. It's going to be how to identify where you're having some issues, what to look for, and where you might be having the issues. So log send queue is one of those. If we haven't gotten the data to the secondary, obviously we're not going to be seeing it. And kind of lastly, redo queue buildup. So once we get the data to the secondary, we actually have to process it, redo it, so that we can actually see it, that it actually gets into the database. And it's not until we redo that we can actually truncate logs or that we can see the data on the secondary. So that's another place where we have latency. In terms of what are some of the symptoms of latency, again, this one acting as a definition and a symptom, I'm not seeing my data on the secondary. That's a pretty common one. There's a couple of reasons for that, not just pure quote-unquote latency due to performance, and we'll talk about that a little bit. Perf issues on the primary. Wait a minute, I thought the secondary wasn't supposed to affect performance on the primary. Even in async mode, we can have some rare situations where we might actually get a little bit of performance degradation on the primary. It's very rare. If I have a synchronous secondary, though, I definitely can have some perf issues on the primary, particularly header sync commit waits, and we'll talk a little bit more about that. Log file growth. If I haven't redone on the secondary, I am not going to be able to truncate my logs anywhere. I am not able to process that until I've done the redo on the secondary. If I am having trouble getting the data over there or having trouble doing the redo process, my logs are going to continue to grow. Longer failover times. So again, if I'm not processing redo on the secondary, which is a major portion of the recovery process, when I do have to fail over to the secondary, I still have to do that redo process if it's not done. And so if I'm having any kind of problems getting the data over there or the redo, I'm going to have longer failover times. So those are some of the main symptoms of latency that we will see. It's always helped me in the past to kind of have a picture of how things fit together so that I can know where to go look if I'm seeing a particular symptom. So I wanted to take a moment to take a step back and say, all right, what is a log block? What are we shipping? You know, how is this all put together? So first of all, we do not ship log records, we ship log blocks. We can think of a log block as a data page for a data file, for a log file, I mean. So essentially, we have our log file, we have the different sections here, the virtual logs, everybody I'm sure is familiar with that. Within a virtual log file, we have different sections of log blocks. A log block, like I said, is essentially like a data page. We're taking log records and storing them on the data page. So we're going to take individual log records, put them on the data page. Sorry, the log block. Those log blocks can be any, I think the minimum size for a log block is 512 bytes, but the maximum is 64K, and that will kind of be based on the activity at the time, and we'll kind of go into that in just a moment. Once we have, because we're not writing log records to the log file, we're writing log blocks. We take those log blocks and we flush them. When do we flush them? We flush them when they are full. Typical scenario there is I've got a large open transaction. I'm writing a lot of log records for that transaction. I haven't committed it yet. As I continue to write records, I'm eventually going to fill up that 64K block. I will flush it when it gets full. I will also flush it when we do a commit. So as soon as we get a commit record for any transaction in that database, not necessarily my thread, we're going to flush that log block. That log block contains or can contain log records from many different transactions, not just my own. So if one of the neighboring threads has a commit and I've got records on that log block, my stuff's going along with that other commit. We also have a group commit as well that what we do is to try to be more efficient in flushing these logs. Sometimes we will wait up to 2 milliseconds before we do a commit. And we've got a wait type for that as well, so we can see if we're having problems just due to waiting on group commit. Normally that's not an issue, and it does help things a lot in AlwaysOn sometimes. So now that we've talked a little bit about log blocks themselves, let's kind of look at the life cycle of a log block as it gets shipped to the secondary. So here's our log block. We've got a couple of commit records on there. It's from a group commit per se. We decide that we want to flush it. So at this point, what's going to happen is we're going to start a log flush, and we're going to send in parallel at the same time that log block over to the secondary. Essentially, we do that by dropping it off to Service Broker, and Service Broker has a queue set up. It's an internal queue that you can't access or see, but basically the log blocks are going to be processed by Service Broker, packaged up into boxcars, dropped on the wire, and sent over to the secondary. That is all done in parallel to the actual flushing of the log block to disk on the primary. We don't wait for the log to be flushed and written to the disk before we actually send it over to the secondary. And in fact, it can be that the secondary can actually write to its disk before the primary has written to its own. Once the data gets over to the secondary, it comes out of broker, we capture it, we dump it to disk, and that completes the hardening phase of getting a log block over to the secondary, with the exception of sending the acknowledgement back. At this point, after we've hardened it on the secondary, two things are still going to happen. We have to send that acknowledgement back. Again, it kind of goes through Service Broker, so we're going to dump the message back into broker. Broker is going to connect over to the secondary, dump and send the message to the primary, send the acknowledgement back to the primary. At some point after the hardening, in a separate thread, we're going to have the redo process that's going to take those log blocks that have been hardened and replay them. That is what makes your data visible on the secondary. That's what actually allows you to connect to the secondary in read-only mode. After the acknowledgement has come back to the primary, if we're in synchronous mode, we're now going to notify our waiting SPIDs that the acknowledgement has come back and that the secondary has hardened the data. That's the important part in terms of what kind of delay or what kind of latency I'm introducing on my primary due to a synchronous secondary, because I have to wait for this whole process of in here of getting the log block over to the secondary and getting it hardened and the acknowledgement back before I allow the clients to move on. And that is essentially another round trip. For those of you who've written your own applications, you know that if you have a lot more round trips, your application performance goes down. And same can be said here. If I have lots of tiny little transactions to do something in my app, I've got extra round trips for each one of those going to the secondary. So you might keep that in mind in your application development. Okay, if we have some time, we will look at the X events associated with the various stages through here. Unfortunately, there is no equivalent to transactional replication's tracer token. I can't just push a button and say, where am I slow? but we do have touch points in almost the whole round trip of X events where we can get a picture and kind of see where things are slow. And if we get time for that demo, I will show that as well. I will definitely have that as a reference slide of the different X events and where they are in the life cycle. So if we don't get to it, take a look at the slide deck and you'll see some of that as well as some scripts that I have. This web link also kind of goes into more detail about the process of the log block and performance issues at different places throughout the process and what you can look at. So that's another reference link for you. Let's go on to some of the causes for latency. Incorrect expectations, and I almost kind of put this in with some humor for it, but in a certain respect it is true. We will have cases of people calling in saying, I've got an application, I make a connection to my primary and I make a connection to my secondary, I commit a transaction on the primary and I try to read immediately from the secondary and I can't see it yet. We don't guarantee that. And in fact, in all of our documentation, we say don't expect that. So sometimes it's just unrealistic expectations of quote-unquote latency. So everything could be functioning just fine. It's just don't expect to see your data 20 milliseconds after you committed it. If you need something like that, then you need to be looking at distributed transactions and two-phase commit type of architectures so that you don't commit in either place until both have committed, and at that point you do have the data on both sides, not using AlwaysOn. So if you need that high or the near zero latency for something like that, that would be a better architecture. Generally, if everything is performing well, you're going to see it within a half a second to a second, but we don't guarantee it. Redo can get behind. So, long-running transactions. So anybody who connects to the secondary is going to be put into snapshot isolation mode. So you are not going to be able to see anything that hasn't been committed. And I've got a demo for that. Regular perf issues. The famous 4 CPU, RAM, network disk. If you're having issues in those areas, if you're undersized, if you're having perf issues in those areas, you're going to have AlwaysOn perf issues. Call out the network latency specifically, again, especially for sync secondaries. Again, because we have to wait for that whole round trip process and the acknowledgement of each log block that goes across. And if I've got a large transaction that requires, say, 15 or 20 different log blocks to go across, I have to wait for each of those log blocks to come back before I can acknowledge back to my client that the transaction's done. So if I have any kind of network latency, that's really going to show up in either the log send queue or the redo queue. And if it's a synchronous secondary, you're going to have problems with header sync commit waits on the primary. Secondary read workload. Just from the pure sense of if I'm doing something, a lot of intensive activity, read activity on the secondary, I'm going to be taking CPU cycles away, RAM away, I'm going to be doing disk I/O. All those things are going to slow down the process of capturing log blocks, hardening them, and replaying them, redoing them. So those can all affect latency as well. And finally, just sheer volume of data. I've got a perfect slide that we'll cover last that kind of talks about just massive data loads and some limitations, and it basically, it can be working as hard and as fast as it can, but we'll still get behind, and we'll talk about why and what it will look like when that happens. All right, let's go in and do a demo for a long-running transaction. So essentially like I said, secondaries are going to come in snapshot isolation mode. So essentially what I'm going to do is I'm going to create a table, insert a record into it, insert a record into another table, wait for 5 minutes, and then I'm actually going to roll it back afterward. and we'll take a look while I'm doing my wait. We'll take a look at the other server. So if we're connected to a primary, I run this. I'm now waiting. I've inserted those 2 records. If I go to, excuse me, if I go to the secondary and I connect, I can see from table 1, my 1 record, I've got a 5 in there. In my transaction, I inserted record 6. I don't see it yet. Well, let me try with a no lock. That's my old trick for uncommitted reads. Nope, still can't see it. It's because we're in snapshot isolation mode. And in fact, I don't even see the table because it's not committed yet. I'm only going to see committed activity on the secondary because of snapshot isolation. Okay. From here, we'll go ahead and close those, get those out of the way. Yeah, we'll go ahead and cancel that. Okay, so the next slide, we're going to look at some Perfmon counters and see what's going on there. All right, so I've put this in report mode first so we can kind of see all the different counters I'm looking at. Beginning with 2012, we have a couple of new sections. We've got the availability replica section with several counters in it. We've got the database replica section. The availability replica section deals more with the infrastructure of getting the data over down into broker, over across the wire. So we're looking at bytes sent to transport, bytes sent to replica, the number of sends to the replica per second. And as you can see, I'm not doing anything in my database right now, so I'm actually still seeing activity going on between my primary and my secondary. All these counters at the top are my primary. The ones here at the bottom are my secondary. And you can see I'm doing on average about 4 sends to the replica per second. That's just background, keeping things alive. We call them Hatter ping messages. We're just keeping things alive. As far as database replica, here we're looking at the number of transactions going across. We're looking at transaction delay, which is another way to look at the Hatter sync commit weights. The transaction delay, oops, sorry, hold on. The transaction delay refers to the cumulative amount of time that we are waiting per second for all of this activity to take place. So we start a timer when we send it off to the secondary, and the delay aggregate doesn't end until we come back from the secondary. So that's what we're measuring there. So, and we've got a couple other things that we're looking at in database replica as well. And then I've added just some stuff from just databases because we're looking at log flushes. Every time we're flushing the log, we're going to be doing something with AlwaysOn, so it's kind of nice to see those together. On the secondary side, some of the interesting counters are log bytes received per second. That kind of tells me how much is coming in. I can see the log send queue size. That's how much is building up. How much hasn't gotten across the wire over to me, the secondary, yet. I have the recovery queue, which is the Perfmon equivalent of the redo queue. When you look in the dashboard, for instance, or some of the DMVs for AlwaysOn, we talk about the redo queue. This is the recovery queue. It's the same thing. And how many redone bytes per second are we doing? So if we kind of fire up some activity here, I'm going to go ahead and just start up. Oh, I'm still doing my log backups. Okay, good. So I've got, essentially what I'm doing is I've got a loop. I'm just going to be updating a record and committing it and going through and looping back and forth. So we'll start that. Oops, sorry. We'll start that. We'll go back to Perfmon. We can now see that I'm doing about 80 sends to Replica per second, 60 to 80 sends per second. That's how many times we're sending stuff down to broker and going across the wire per second. We can see that I'm sending about 100K of bytes to the secondary per second, and actually a little bit more is actually going down to the transport layer because we have to package it up, boxcar it, things like that. So it will always typically be a little bit more than the bytes sent. The mirrored write transactions, we're seeing about 50 to 70. Again, that should be pretty close to this sends to Replica, but we got some other things that go through as well. So sends to Replica will be usually a little bit more than mirrored transactions. And this transaction delay, again, that's the total amount of time that we are waiting for all those transactions to come back. So if you kind of want to get a quick aggregate average of how much per transaction I'm waiting, I can take this transaction delay and divide it by the number of transactions, and I can get my delay per transaction average. And it looks like I'm anywhere between 1 millisecond to maybe 5 or 10 milliseconds, depending, and it'll fluctuate around a little bit in my environment. Okay, we can see here that I'm doing about 300K of log bytes flushed per second. I'm only sending about 100K. That's due to compression. We try to compress things before we send them. On the secondary side, we can see here bytes received. Again, that should match pretty much the bytes sent. If this is lower than bytes sent, I've probably got some sort of network issue going on. Again, if I'm looking at the database level, now I've got log bytes received. That's pretty close to this value. So if I grab here, those are going to be pretty close to one another. The differences are just going to be in timing of when we grab from the DMVs. Now we can also see here the redone bytes per second, which typically will be a little bit slower than what we've got coming in. So sometimes we'll have transient queues of a little bit of the redo queue. As long as it's transient, it might go up to a meg or 2 meg or 10 meg, come back down. As long as it's transient and going down, you don't have to worry about it. It's when it starts building up for long periods of time that it becomes a problem. Hello, come on. Shrink back down. There we go. Sorry about that. Okay, so let's go on to the performance counters. Okay, yeah, there's still something I want to show here on this demo. All right, so actually I'll take that back a little bit. No, actually I'll go do it now. All right, so what I'm going to do now is I'm going to cause a scenario where I'm going to cause a blocking scenario on the secondary, redo blocking. So what redo blocking is if I have some DDL that takes place on the primary and I've got some read queries that are going on in the secondary holding some shared schema logs, I can cease and cause blocking of redo. So let's demonstrate that real quick. So come here, create a table, put some records in it. We'll go to my secondary and I'm going to run a query on the secondary. So this query is now running. If we also go to the secondary, we can see here that we've got schema stability locks that are granted. I do not have any blocking at the moment going on, but now what I'm going to do is I'm going to introduce some blocking. So if we go back here to the primary, I'm going to do an alter statement, alter table, change the data type. We can see that that successfully completed, so there was no blocking on the primary, nothing to get in the way on the primary, it happened. But now when I go to the secondary, I'm going to see that session 61 is blocking 62 that section 62 is my DB startup. That's my redo thread for that database. Now, if I look at why I'm being blocked, because I want to schema modify. I need to be able to change the schema on the secondary, and I can't because of the schema stability locks by the other read query. So if I've got a system that's got a lot of heavy-duty reads on it and long queries, and I have to do some DDL on the primary, I can run into a blocking scenario. So now let's look at what that looks like in Perfmon. We can first, in table mode, we can just see I have this recovery queue is building up. It's up to 10 meg now and continuing to rise. We can also see that my redone bytes per second is 0. It's not doing any redo anymore. There's also a perf counter that shows redo blocked per second. I just don't have that one on there, but that one's another way that you can take a look and see. Let me go ahead and increase my throughput of what I'm doing. So I'm going to cancel this and get rid of my wait for and just open the floodgate, do a lot more activity. And I'll switch this back to line mode. And I can look at my recovery queue, and we can see that it is continuing to rise. Now I'm going to go ahead, I'm being throttled still somewhat because I am in synchronous mode, so my secondary is kind of slowing me down a little bit. So I'm going to switch the secondary to async, simulating a server that's far away, and you can see now my redo queue is going way up really fast because I've opened up the throttle on the primary. If we go back to report mode for a second, we've gone from 60 or 80 sends per second to 1600. I'm doing a lot more, and I'm now doing 2 megs per second going across the wire. So I've really opened up the throttle because I'm not waiting on the secondary anymore, but now my recovery queue is getting huge. So if I'm seeing that guy continuing to climb over time, I've got a problem on the secondary, and I got to fix that. Because simultaneously what's happening is my logs are not truncating on the primary. So that could be a real major problem for me. Okay, let's kill this guy. And we can see that levels off, and eventually redo processing will take that and bring it down to 0, and it'll catch up. Okay. That pretty much concludes that one. So let's go and talk about some of the wait types that we have. For those of you who've been doing performance troubleshooting for a while, we always know go look at SysDMOS wait stats. What are we going to see in systems that are dealing with AlwaysOn? The types that we're going to see are header sync commits if you are using synchronous secondaries. You're going to get a header sync commit every time you commit a transaction. Actually, every time a log block goes over, you're going to get a header sync commit wait, because we have to wait for it to get over there. It might only be 100 microseconds that we're waiting, but we're going to have a wait every time we go over there. So for the most part, your wait count for header sync commits is going to go up 1-to-1 proportionally for the number of transactions that you're going across, or at least the number of log blocks that are going across. If you've got really small transactions, then it might be the number of transactions is the number of log blocks. If you've got large transactions, it's going to be based on the number of log blocks, not the number of transactions. It's the duration that we worry about the most. It's not the fact that we have those waits, it's the duration of those waits that's the problem. Again, that you can be looking at those values with Perfmon and that transaction delay counter. Header synchronizing throttle. What this is an artificial wait that we impose on transactions on the primary because the secondary is way behind. If, for instance, I was doing some maintenance and the secondary was down for 30 minutes or an hour, and I'm I have a system that's a really busy system doing 20,000, 50,000 transactions per second. I'm going to build up a substantial log send queue, and we're going to know that. And so when the secondary comes back after the maintenance, he's behind. We're going to keep track and know how far behind it is. We're also going to keep track of the transaction rate coming in. And if we feel that it's too much for the secondary to be able to catch up, we're going to introduce a throttle to the primary initially of 2 milliseconds that says, hold on, just wait 2 milliseconds before you commit this transaction, just to slow down the primary a little bit to give the secondary a chance to catch up. Normally we don't see this much of an issue, but it is there. There is an X event that will kind of show you if you're running into it and by how much. It can go from 2 milliseconds all the way up to 20 milliseconds per transaction to slow things down, trying to give the secondary a chance to catch up. So watch for that one. Header group commit, again, that was when we're doing group commits, essentially that is the time it takes from that we're waiting when this commit record came into the log block until the log block actually flushed. That would be a header group commit wait, because we're waiting. We should have just gone ahead and flushed, but we didn't flush because we were waiting to see if something else came in and then flushed. So that amount of time while those other records come in, that's the amount of the group commit wait that you're going to see. Usually that's not too bad at all. It's usually not anywhere in near the top 10 of your wait types. But if it does creep up in there, give us a call. I actually haven't seen a case where that's a major problem yet. So if you do have one where that's high, I'd like to know about it. I'd like to take a look. And finally, of the most important ones, redo thread pending work. In one sense, this is an important wait type. In another sense, it can usually be ignored. If I have a system that's fairly idle, then redo thread pending work is going to actually be kind of high, because what it means is I'm sitting there waiting to do some work. I don't have anything to do. I don't have any log blocks coming in to process. So if it's an idle system, that's okay. If it's a busy system, that's not okay. That means my log blocks are not getting there for some reason, or they're getting there much, much slower than they should be. It's emptying out the queue and then sitting there doing nothing, waiting for more log blocks to come in. So it really kind of depends on the context of the situation as to whether or not it's a problem. But if you do see it, you could have problems. Now, if it's a busy system, redo thread is pending work, and that value is high, it probably means that we're having problems flushing the logs, receiving the logs. If it's a busy system and that's low, and you're still not seeing data, then I'm not seeing a redo thread pending work, which means redo is actually doing something, but I'm still not seeing data, so why not? And that kind of brings me to my last slide. This one, and I apologize that this one's fuzzy, but I'll walk you through what we're talking about, and we'll zoom it up to kind of take a look. This is from an actual case. We had a customer that was complaining that their data load, they had a massive data load at night. It would finish typically like 4 o'clock in the morning, but they wouldn't be able to see all their data until 8 o'clock in the morning, 7, 8 o'clock in the morning. It's like, why? Well, it was a combination of several different things. One, this green line is the recovery queue. Again, on the secondary, that's the redo queue. That's how fast or that's how much logs have not been redone yet. That's how far it's getting behind in doing the redo. And we can see here that it got all the way up to 80. The scale for this guy was gigabytes, so it got up to 80 gigabytes of redo queue. Why did I have a redo queue that was that high? Well, let's take a look some more. This black line here is the number of redone bytes per second. That value, go away, that value was 10 megabytes per second. It was doing 10 megs per second of redo queue. While we had this log synth queue, we had to backlog at one point as well of actually getting the data over there. But while we had incoming data to the secondary, we were coming in at about 20 megabytes per second. So this log bytes received was 20 megabytes per second on average. That's 10 megabytes per second higher than we're able to get it out the door with the redo queue. So basically, I'm getting further behind by 10 megabytes per second for this whole period of time, and that's what causes my redo queue, my recovery queue, to continue to grow. At this point, my incoming data ceased. So my load on the primary finished at 4:12 in the morning. So I didn't have anything else coming in from the primary, anything new coming in from the primary. All the data was there. We just needed to finish processing it because here's all my redo backlog. I haven't finished processing it. And like I said, if we haven't redone it, you can't see it yet. So what was going on there? Why was it taking so long to redo? Well, it's because of the way we do redo. If you look here at the redo line, we see a little bump in performance here. We get to about 12 megabytes per second. Then we see a little bigger bump to about 15 megabytes per second, then 20 megabytes per second, and then close to 30 megabytes per second here toward the end. There's a couple of reasons for this. One, the transaction types changed toward the end. So this portion of the redo log, we had different kinds of transactions going on at this point in time than we did earlier on in the process. Same thing that was going on here. Redo is how long redo takes is a function of the types of transactions and the number of redo logs. Excuse me. The number of redo logs on the log blocks themselves. I'm sorry, the number of log records on the log blocks. Very, very full log blocks with tons of tiny transactions can cause a lot more processing, and large transactions with few numbers of log records but impacting lots of data pages can also cause the redo process to slow down. So it's the nature of the transactions, but also with it was the CPU utilization in this case. Here we see this pink line is the overall CPU utilization of the box. They had like 80 cores in the system. But this core up here was the core that the redo queue was going on, and it was pegged between 95 and 98% the whole time. Remember, redo currently today is still a single-threaded operation. So essentially, we just had so much sheer volume of changes coming in that redo could not keep up. We didn't have any disk or network or RAM bottlenecks. We basically were open full throttle and just using that CPU as hot and as fast as it could go trying to process redo. And there wasn't anything that we could do for this customer other than to tell them change how they're doing things, with even the possible option of taking the availability group out, taking the secondary out during the load, restoring a differential, and then re-adding it back in. But basically, bottom line, the redo portion just was capped. It couldn't go any faster, and it was a CPU bottleneck at this point, and it's because it was single-threaded. So I guess kind of the overall intent and hope out of this presentation was to give you an eye on where we look for things in the process and give you a chance to kind of see some of what we've done. Coming back to this, There's a lot of different moving pieces in this section. We're flushing, we're sending, we're in the sending process, we're dumping it down into broker. Broker is encrypting it. We're also compressing during this time frame. We're having to decompress on the box, decrypt on the box before we write it to disk, sending the acknowledgement back. So there's a lot of moving pieces throughout this whole environment. So hopefully I've given you a taste on that. What I'll do is I'll open it up for some questions, and then if we have some extra time, if there aren't very many questions in there, then I'll try to show you a little bit of some of the X events that we have, and we'll go from there.
All right, so first one is somebody asked, what is the exact wait type for group commit?
The exact, you mean what does it look like if I'm querying it?
Right,
It's
yeah.
a header group commit. That's what it'll look like.
Okay.
In wait stats, that's what you would see, header group commit.
I think that's what they were asking, yeah.
Okay.
For a synchronous secondary, should I expect to see data on secondary as soon as I receive the commit acknowledgement on the primary? If not, could latency be due to the redo process?
If you're not seeing it, it could be due to redo. It could also be, so yes and no. You can expect to see it fairly soon after you've committed it and received the acknowledgement, but 50 milliseconds might be an unreasonable expectation. 1 second, 2 seconds in a system that's keeping up, yeah, that's normally perfectly reasonable. If you're not seeing it in that point in time, it's typically redo is either slow or redo has gotten blocked, which is very slow. It's not advancing anymore. Or it could be because of an open transaction, that if the transaction actually hasn't committed, you're not going to see it. So if the transaction's closed, then it's probably redo as the reason you're not seeing it.
Okay. This one, of course, some of these are going way back earlier in the presentation. I think you actually kind of already answered this one, but you can reiterate it. If one needs to patch and reboot the secondary, how long can it be out of service and still automatically get back in sync?
That's up to your ability to contain log growth. So just know that when you are doing the maintenance, anytime a secondary is slow, it's going to hold back truncation of the logs on the primary. And this goes for all secondaries. With 2012, you can have 4 secondaries. With 2014, you can have 8 secondaries. The slowest secondary is going to be your bottleneck on log truncation. So if you've got a secondary in Sydney, in your primary, Sydney, Australia, and your primary is in New York, and you've got a really bad latency between the two, that one in Sydney is going to affect your log truncation, whereas the secondary is in the same data center as the primary might not. So the logs have to be processed on all secondaries before they can be truncated on the primary. And essentially, it's really up to how long you can withstand the logs growing. If you can't, like on that one Perfmon I showed where their redo queue got up to 80 gigs, well, that meant their log didn't truncate for at least 80 gigs. It could have been more than that. So if they could handle an 80 gig log and they were fine with it, it's not a problem. It'll catch up. But it's really up to you and how much disk space you have.
I still can't believe that 80 gigs, man. That's crazy. Must have been a very busy load.
Yep.
Can a high number of VLFs affect the performance of the log blocks being transmitted to the secondary?
Yes and no. It's not so much the transmission as the other steps around it. So when we flush, we actually we have what's called a log pool manager now. And so a log block is cached in this log pool manager. So we actually have to get an open log block in the cache, and then we have to then go store that in the appropriate log file, virtual log file, when we start dumping it down to disk. And we can have some contention in trying to figure out which virtual log it's going to. So the more virtual logs you have, especially if they're small ones, the more we have to search through our virtual log directory, if you will, to figure out where it's got to go. And then that part can be slow. The transmission of the log block itself is more up to just networking capabilities than anything else. So yes, more virtual log files can affect performance because it can affect the time to flush and the time to get the log cached to be able to dump it into AlwaysOn's broker. But the actual transmission itself isn't where the bottleneck is. It's grabbing the cache and dealing with it there.
Let's see. How do you unblock a redo block?
You kill it. You kill the blocker, just like any other blocker. You either wait for it or you kill it. When I was showing here, let's just change this back. Let's see, we'll get this going here. We can get my query going. So I have this query that was still running from before. I have this query running, and if I go do, come on, if I do a DDL statement again on the primary, you can see here that I'm going to have blocking, and the wait type that I'm waiting on is a schema modify. The redo thread needs a schema modify to be able to keep going. And who's blocking it? That query. So it's just a traditional type of a blocking. What you do to get rid of traditional blocking, you have to kill the offender or wait for the offender to finish. In this particular case, this query might run for a couple of hours, so I would kill it. And you could set up scripts on your own to look for blocking and look for offending SPIDs and kill those SPIDs. That's kind of what we recommend today, if you have a major problem with it. It's not normally an issue. It's when you have basically a lot of DDL changes as well, because the blocking doesn't happen until I made some sort of DDL operation. But notice the DDL can be anywhere that I have DDL that I have a conflict with my lock. So if I'm inserting records into a different table that I did no DDL to, the fact that I've got a lock conflict here on the same object is what's causing my blocking. So it may not be, it might be just a fluke that I've got one query running for a really long time on the same object that I happen to have modified, and that set up my blocking scenario. So it's pretty rare that people run into it, but people do. The resolution is kill it like you kill any offending. Hello? Did I lose people?
Nope, sorry.
Okay.
Good old mute button always gets me. Somebody asked, in that last Perfmon, how would you identify the processor of the redo log, or how did you do that?
Yeah, okay, excellent question. So here, if I do from exec sessions, exec requests, where command equals db startup, let me get everything here. Okay, so here's all my stuff, and my scheduler ID can then tell me where I'm at. So if I can go from select star from sys.dm schedulers, and I know that scheduler ID 0 is CPU 0. And I was able to confirm by looking in Perfmon, because I knew which, where's my slides? I knew which CPU I was looking at, which was hot here. This was processor 10. I knew that because, I could see that that guy was hot, but I went back, looked, and saw, all right, well, did I have a DB startup thread running on scheduler 10? And I did. So it's like, okay, that's my guy. That's DB startup. That's what's causing my issues.
Let's see. Is there a session SPID that corresponds to the redo process, given that it's single-threaded? Is that something like you can monitor? I guess he's asking,
Yes,
is there
and
something dedicated?
yeah, yes and no. If I have long periods of inactivity, or if I change to not read on this, well, no, that might actually do it. But if I have periods of inactivity, that thread's going to go to sleep, and that process will shut down, and then it'll start back up again when there's some new activity, and it may not have the same session ID later.
Gotcha.
So as long as it's busy, it'll keep the same session ID. But if you have periods of idleness, it might change on you.
Let's see. Do you have any experience with column store and availability groups with a primary and forum or secondaries?
Unfortunately not. Nope. Sorry about that. If they have a specific question, they can shoot it to me and I can research and try to get an answer for them though.
Gotcha. I think it's all the questions we have, so I think we can kind of wrap it up there. A lot of people thank you for the presentation, that it was extremely helpful for them, so always glad to see that. So with that, Tracy, thank you again for taking the time to talk to us today. I know everybody appreciated it. It was really great stuff. So
thank you, my pleasure. And like I mentioned before, scripts will be available, the slide deck will be available, as well as I've got some scripts for some stuff that I would have loved to have shown, but just we didn't have the time for it. So I'll try to get that documented up so that you can kind of go through it yourself and take a look at it. And my email was on the first slide, so if you guys have questions about my scripts, feel free to reach out to me and email me. I'll be happy to respond and reply.
awesome. Thank you very much. And everybody, if you want, you can go ahead and jump in the next session, and we'll see you over there. Thanks.